Hello, welcome back to ECE484, Fall 2021. Okay, so where were we last time? We've been doing direct design, and so this is where, again, you discretize the plant. We always discretize our plant using the step invariant transformation, and then we design the controller in discrete time for the discretized plant. All right. The technique we've learned so far has been pole placement, and it's been very much similar to what we've done in continuous time. Okay, the basic ideas are, certainly the concepts are exactly the same. There are some what I would call superficial differences in some of the equations. Okay, and in particular, last time we looked at pole placement with step tracking. And we, just like continuous time, broke it down into two cases. There was the asymptotic tracking case, where you want 0 steady state error. And there you use a discrete time version of the internal model principle. And the basic idea is that you take your controller, your digital controller, you embed an internal model of the unstable part of your step. Right? So there's the pole at z = 1. And then you have this extra term, d1, and you use regular pole placement to design d1. Okay? Keeping in mind that in discrete time, the way that we pick the desired z-plane poles, there's a kind of an extra step, which we saw last time. Then we talked about practical tracking, which again just simply means non-zero steady state error. And the idea here is that you increase the order of the controller, you make it equal to the order of the plant, and then you just add this equation, which is the essentially bumping up or making sure that the DC gain or the steady state gain of your controller is sufficiently high to get low steady state error. Okay? And this was the equation, and we spent some time deriving that. Okay? So we're going to continue from there. We're going to do an example of this one. Okay? I haven't done that many examples in this section because the examples would be so similar to what we did before, right? We did an example of picking the poles in the z-plane, because that's kind of really the only thing that's different in discrete time. But this, we'll do an example of this because the equation is, again, a little bit different. Okay, so we're going to do example 822, okay? And this is an example we've seen before. So in example 332, we did practical step tracking using pole placement, but we did it all in continuous time, right? We just designed the controller in continuous time. We had the practical step tracking constraint. We're going to do the same example again, but we're going to do it in direct design approach, okay? So we're going to first discretize the plant and go from there. Okay, so this is our plant, like so. The specs are closed loop stability, goes without saying, but I said it anyway. We want 5% step tracking error, so the maximum allowable error is 5% the size of the step. Overshoot less than 20%, and settling time, less than or equal to 20%, and settling time less than or equal to 4 seconds. Okay, and we're just going to go through the steps of doing a direct design. Right, so let's do that. Step 1. In direct design, the very first thing you're going to do is you're going to discretize the plant, which we learned how to do in Chapter 7 by hand. But in practice, you'll typically do this with MATLAB. So we're going to discretize the plant. Okay. I guess I didn't write it down, but let me say that the sampling period is going to be 0.05. Okay, of course, I need that information in order to do the discretization. Okay, so I'm going to write P sub d of z, which is going to be our notation for the step invariant transformation, C2D, the default method in MATLAB. In this case, I'm actually going to use MATLAB to do it. And what do we get? We get the following. I'm going to keep a lot of significant figures here just because the numbers are quite small. So there's our numerator. And our denominator is second order. And so again, at this point, I'll remind you that the advantage of doing direct design versus emulation is that we are exactly discretizing the plant at the sample moments, right? So there's not going to be any issues. If the discrete time system that we design works well, we expect that the continuous time system, or the sample data system, will work well, at least at the sample points, right? That's the advantage. The sampling period, the A to D, the D to A, their model is embedded now in our plant. Okay, so we proceed from there. And now it's just essentially pole placement. So in continuous time, what would we do? We would characterize the good region and pick desired poles, right? So I'm going to do that again, but remember that for picking desired poles in the z-plane, what we do is we use our continuous time equations, and then we map them over using the exponential. So characterize the good region. And I'm just going to mention that this is literally exactly the same as example 332. So I'm just going to write it down. It comes from the settling time and the overshoot. So this is same as in example 332. And I won't belabor the point. Let's just write it down. You want them sufficiently far to the left to get the settling time spec, which was 4 seconds. And you want to restrict the argument of your pole locations to be sufficiently large. And in this case, theta max equals 1.1 rads. Okay, and as always, this comes from settling time. This comes from overshoot. Okay, so that part's the same, so nothing new there. Okay, so what do we do next? We determine the structure of the controller. Right, all the comments I said in terms of continuous time apply here, right? You need to pick the type of controller you want before you pick the desired pole locations, because the order of the controller informs how many desired poles you have to pick, right? So if you're doing internal model principle, you'll get some order of the controller. If you're doing practical step tracking, you might get a different order. So at this point, we want to fix the structure of the controller. So determine the structure of the controller. All right. This example, we're doing it in the section on practical step tracking, so I'm going to do practical step tracking. Okay. Okay, and so what does that mean? Well, there's our plant above, the discretized plant, second order. So we're going to pick the controller to be the same order as the plant, right? This is going to give us those extra tuning knobs that we can use to simultaneously place the poles while also setting the steady state gain of the controller and meeting the tracking specification. Okay, so the controller will be second order. Screw up the indices there. There we go. There's our controller. And that's the structure we're going to go with, okay? So now that we know the controller structure, we can pick desired pole locations. Okay? And also steady state gain. and steady state gain. Of the controller. Because remember, we're doing practical step tracking, so we have that parameter, that delta parameter that we get to pick. Okay, so second order plant, second order controller, let's pick 4 poles. And remember how we do this. We first pick the S-plane location in the good region. So there'll be 4 of them in this case because, again, plant and controller are second order. So I will pick, as always, 2 dominant complex conjugate poles. Okay, and then our non-dominant ones further away. So this will be, let's say, this. So these are the dominant, non-dominant. Okay, that's S-plane, but we're doing direct design, so we need desired Z-plane locations. So remember how we do that. We take these S-plane locations and we map them using the fact that the step invariant transformation does some, we've studied how it affects poles and eigenvalues. And so this generates the Z-plane location. Okay, those are ECEs, and I remind you, I'll be quite explicit about this, we're going to take each lambda multiply it by the sampling period and then exponentiate. Okay, sampling period here was 0.05, so we get the following. Those will be our dominant poles further away from the origin. Right? In discrete time, the dominant poles are the ones furthest away from the origin. And the non-dominant ones will be closer to the origin, closer to 0. And so in this case, we get okay. So that's going to generate our desired characteristic polynomial. So let's write it down. Okay, I'm going to multiply out all of those ECEs to get my desired characteristic polynomial, so let's just write it down. We get z to the 4 in this case, minus 3.0205 z cubed plus 3.3791 z squared, oops, minus. Sorry, the numbers are not so nice, of course, to write down, but typically you're going to do this on a computer anyway. So, okay, so there's our desired characteristic polynomial. Again, oh, where was the sampling period specified? So the sampling period is specified right here. It was given, basically, in this case, 0.05. I wrote this sentence, or I got to here, I think, and then I added that. I realized I hadn't included it. Okay, I remind you though, again, in discrete time, it's not necessary that all the coefficients of this polynomial have the same sign, right? In continuous time, we'd say, hey, wait a second, this polynomial is not Hurwitz, not stable. But remember, in discrete time, it's the different tests. We're not using the same tests as continuous time. So this certainly is a stable, or sure, we called it, polynomial. It has these roots. Okay, so we have to pick this delta parameter. This delta parameter, you know, is our last equation when we're doing practical step tracking. So delta, pick this delta value greater than or equal to R naught over ESS max, which is 1 over the 5% maximum tracking error, minus 1, and this is equal to 19 in this case. Okay, this was given in the specs. Okay, so let's use equality. I mean, I could pick a bigger value, but let's just use equality. Let's use delta equal to 19. It's a design choice. And remember, we want to add this equation, which is d of 1 times p of 1 equals delta. And so you go back and you look at your discrete time plant and you say, oh gosh, I've got to figure out what p of 1 is. The steady state gain of that plant looks like a pain, right? I have to sub in z equal to 1 and do some bunch of calculations. But remember, the C to D discretization is exact. So the DC gain, or the steady state gain of the discretized plant, will be the same as the steady state gain of the original continuous time plant. And there we sub in S equal to 0, and we get 1 over 0.25, which is 4. Okay, so it's going to be the same in discrete time. So note that P sub D of 1 equals 4, same as P of 0. Okay, so it'll have the same steady state gain. Okay, so basically we've done we've made all the choices that had to be made in terms of pole locations, controller structure, the value of delta. The rest is just mechanical at this point in the sense that we just have to solve the design equations. So let's do that. Set up and solve the design equations. I'm going to copy the plant because it's going to be useful for us. So let's copy this expression. Because the coefficients of that numerator and denominator we're going to need when we set up our design equations. If you sub 1 into... Right, but in continuous time, the DC gain, the steady state gain, so the question is, if you sub 1 into the continuous time plant, you don't get 4. But it's continuous time, so you don't sub in S equal to 1. You sub in S equal to 0, final value theorem, right? You plug in S equal to 0 in continuous time. In discrete time, you plug in Z equal to 1. That's the difference. So that's why I wrote same as P of 0. Remember, there are superficial differences, but it's analogous, right? And so when I say steady state gain, yeah, okay, great. Okay. So there's our plant. Let's write these big equations. I'm going to leave myself a bit of space because these numbers have a lot of digits. Okay. So we want to solve for the controller gains. So the gains are okay. On the right-hand side, so this matrix over here, or this vector over here, we get that from the first part, at least, from our desired characteristic polynomial. And so I'll fill that in. So I might have not left myself enough space, but let's just write it this way. Okay. And remember, that last equation is going to come from our steady state equation. So let's, as before, write this kind of partition. And remember that last equation, we write it so that the right-hand side of the equation is 0. Okay, so let's fill in the matrix. I like to partition it into these different blocks. So we'll do this block first here. This comes from the denominator of the plant. So that's why I put it over here. So look at those coefficients, and they're going to generate the columns of that part of the matrix. So let's see if I can fit this. 1, negative 1.951, 0.9512. Okay, those are the three coefficients from the denominator, and then we pad with zeros. Okay, and we shift down. Sorry, it's kind of hard to fit everything on the screen here. But these are the same numbers. They might look a little bit messy, but the same numbers just shifted down. And then we do the same thing again. Okay, so they come from the denominator of the plant, and we've got them there. This next part of the block comes from the numerator. Okay, so we do the same sort of thing. So there's no z squared term, so that's that 0, and then we just continue adding. So so this should be a 0. I think I wrote this down. Let me fix that. I made a mistake here in this expression. This should be a 0. Right? So it's tiny numbers, so you got to be careful. So that was a 0. The point still stands, though. But pad with zeros. Okay, so this is going to be tricky to fit. I'm sorry that I'm writing so small. Okay, that's from the numerator, and then we shift one more time. Okay, I'm not going to be able to fit that, so let's just say that that all goes there, and that goes there. Okay, so leave it like that. Okay, and the only thing kind of different here is that we need to plug in this last equation. So remember, the last equation that we're trying to incorporate is this equation. In this case, PD equals delta. Okay, we know PD of 1 is 4, and delta we chose to be 19. So what we saw last time when you rearrange this equation, what you end up getting is the delta's over here, multiplying the F coefficients, and then P of 1, or PD of 1, which was 4, multiplying those equations over there. Okay, and as always, if the plant numerator and denominator are co-prime, meaning they do not have common zeros, common roots, this equation has a unique solution. Okay, and if in this case, if you solve it, so again, you solve for the gains, the f's and the g's, and you plug them back in, and you will get the following controller. And you can check that D of 1, PD of 1 equals 19 as expected. So we should hit that spec for the tracking error. Just hit it. Okay. And the nice thing about direct design is that because we did the discretization at the front, there's nothing to do at this point in terms of implementation. I do not need to pick a discretization method anymore. Now I just implement D as either a difference equation or a state space model. And we've done our design. Okay, so direct design pole placement. Again, it looks like we're doing the same thing. Like you say, what is the difference? The difference is we've discretized the plant. We expect there are no approximations being made. At no stage are there approximations being made. Okay, so if our plant model is very good, then this is going to behave, when we implement it, it's going to behave exactly as we see it in simulation. I mean, of course, there'll be modeling errors, but that's a separate issue. Okay, so the last thing we'll do in this chapter is control design in the frequency domain. I think I just have a bit of a technical issue here. 1 second. Okay, sorry about that. I will fix that. Okay, control design in the frequency domain. The basic idea here is that we have some established tools in continuous time for doing frequency domain design. Lead, lag, lead, lag. Okay? We don't want to throw away that knowledge that we have from continuous time. Is there some way to make that work in discrete time? Okay? And that's what we're going to talk about here. But the first issue is that Bode plots for discrete time systems are messy. Right? I didn't even bother, we don't bother, I didn't teach you how to draw them by hand because it's too messy. Bode plots in discrete time are messy. Okay? So we don't want to be drawing Bode plots of discrete time systems. And in particular, it means that our nice design procedures or methods for lead, lag, and lead lag controllers, they don't port over to discrete time very simply. Okay, so how do we do this? How can we design these controllers in the frequency domain? Okay, what we're going to do is we're going to do the same sort of trick we did to be able to use Routh-Hurwitz. Okay, and we didn't cover it in class, but it was in the problem sets, and I mentioned you should read that section. But the idea there was that the Routh-Hurwitz test is really built for continuous time systems. So what we did in the Routh-Hurwitz test is we used the bilinear transformation to make a discrete time problem look like a continuous time problem. And we're going to do the same thing here. So to overcome this problem, we will use the same approach. We'll use the bilinear transformation. In the same way we did when applying the Routh-Hurwitz criteria to analyze stability of discrete time systems. Okay, and so what we're going to say is I'll remind you what the bilinear transformation is. So it gives a relationship between what we would normally say S, but I'm not going to use S, and I'm going to mention why in a second. It gives a relationship between the continuous time sort of transform variable and the discrete time transform variable. And that relationship is the following. Okay, so this is the discrete time, this is the bilinear transformation. With t equal to 2 from chapter 4 and v in place of s. Okay, I'll write it down in a second, but I'm purposely choosing a different variable than s because I don't want you to think, remember we're doing design in discrete time, so we're starting off with a continuous time plant in terms of s. We discretize it to get a plant in terms of z. I don't want you to think we're going back to the original continuous time plant when we do the way we apply the bilinear transformation here. That's why I'm going to use the symbol v. So the procedure is the following. Okay, we are going to discretize, we're going to first discretize the plant. Get PD of z using the step invariant transformation, okay, just like before. Then we're going to convert that discretized plant to a plant in terms of this v variable, okay? I'm going to use the bilinear transformation to make it look like a continuous time system. I'll have more to say about this, but I'm not undoing the discretization. Okay, we're just using the properties of the bilinear transformation because it has some nice properties that will help us do design. Okay, so I'm going to set P of V equal to P sub D of 1 plus V over 1 minus V. Okay, I'm going to design the controller using the same techniques from year 3, also the appendices of our course notes, for this plant, P of V. Using existing frequency domain design methods. Okay. When you're done, you turn it back into a discrete time controller by undoing this V transformation. Okay. I want to emphasize, this is not emulation. Okay, we are not using the bilinear. So this is kind of a subtle point, right? So I want it to be clear. This is not emulation. We are discretizing the plant. So at this point, oops. At this point here, we have taken into account our sampling period. We have now got a discrete time plant. We are just doing this maneuver here to be able to use our design equations. And I'll explain why it's going to work well. But it's not undoing the discretization, right? This thing here is not going to be the same as the original P of S that we started with. Okay? It's only to enable design. And at the end, we're just undoing that transformation that we applied. Okay? So that's important. Okay? And I want to emphasize, I'm going to emphasize it even further by adding a little remark. That we purposefully use the symbol V here to make it clear that we're not undiscretizing the plant. in step 2. Okay. Okay. So the question then, the natural question is this a good strategy? Like, I mean, certainly you could try this, right? I'm suggesting we should try this, but is it a good idea? Like, is it going to work? Is this a good strategy? Yes. Here's why. Okay, so there's a bilinear, so that's right, it's going to preserve the stability. I mean, what's going to happen is, the question is, does the bilinear transformation preserve stability margins? And the answer is essentially yes. There's going to be a very simple relationship between the stability margins in the V-plane and the frequencies and so on, and in the discrete domain. So the answer is yes, and that is exactly right. That's why it's a good strategy. So, indeed. Okay, so let's draw the pictures just to keep in mind what's happening here. So on the one hand, we've got our discrete time system. And then what we're saying is that we're just going to treat this thing as if it were continuous time, but not by doing, not by using the original plant, but rather this kind of fake plant, if you will. Okay, so why is this a good strategy? So the first is that it preserves stability. We already know that. Okay, which means that if we design C of V to be stable, then we know that D of Z, or if we design C of V to stabilize the loop, then we know that D of Z is going to stabilize the loop. So by that I mean closed loop stability. Okay. This is not like emulation, right? Emulation does not have that property, and it's because we're mapping over both the controller and the plant using the bilinear transformation back to the Z domain. All right? 2, the steady state calculations are preserved. Okay? In other words, if you design C of V to achieve a certain value of tracking error in steady state, then your D of Z will achieve that exact same value. All right? So the value, let's write it here. Of the steady state tracking error is the same in both domains. All right. And finally, as was asked in the questions, there's a simple relationship between the frequency in the Z world and frequency in the V world. there is a simple relationship between gain and phase crossover frequencies of the V version of the controller in the plant and the Z version. Okay. And let's just look at this in a little bit more detail before we do an example. So, do you see this? Pick a complex frequency. So let theta be a number between 0 and pi, and set Z equals e to the j theta. Remember, in discrete time, that's how you do frequency response. You pick a point on the circle, and that corresponds to essentially a complex frequency, or a frequency in discrete time. Okay, when I run this through this bilinear transformation, what do we get? Okay, do a little bit of algebra, and you will get the following. You get a point on the imaginary axis. So we can think of this as like a frequency. Right? J times omega, that's how you do frequency response in continuous time. Okay? So frequencies in the discrete time domain, theta, let's call it, get mapped to frequencies in the continuous time, or the V domain, through this simple expression here. Okay. And so in particular, if you have the desired gain or phase margin at a particular frequency theta, or omega, sorry, in the V world, that's going to generate the desired gain or phase margin at theta. All right? And so in particular, have acceptable stability margins at gain crossover and phase crossover then C of V, P of V will have acceptable stability margins at, well, use that expression above, right? Omega GC. And vice versa, right? And so that's the reason, that's the basic idea. This is going to work because frequencies get mapped over in there's a simple relationship between frequencies in the V plane and frequencies in the Z plane. Okay, so I'm going to do an example now of this, but keep in mind the basic idea. There's not much to it, right? There's just this one little extra step. Well, there's the it's here. We're going to basically follow this procedure, and I'll talk about, like, for example, this step. This can all be done in MATLAB, right? So this is all stuff that you can automate pretty quickly. So let's do an example. So our plant is given by the following. And our specs are, if my reference is a step, I want that ESS be less than 5%. So 5% tracking error on steps. And let's say I have a desired phase margin of 60 degrees. For good robustness. Tolerance to delays. Okay. But it's a given spec in this example, all right? So what we want to do, of course, you could try to do pole placement, but in this section we're going to do frequency domain design. We're going to illustrate this procedure that we've introduced. Okay? Our sampling period is t equal to 0.05 seconds. Okay? Sometimes the sampling period is fixed by considerations other than control, right? Sensors run at a particular frequency and you can't do anything about it. Okay. Or, you know, the computer is doing other things besides feedback control, right? So you don't can't dedicate all the resources to doing the control. Okay. So from the specs alone, I still have a lot of choice here. Even if I decide I want to do frequency domain design, I could do a lead controller, I could do a lag controller, and I could do a lead lag controller, right? All three controllers can handle this type of spec. I'm just going to, you know, choose one, and I'm going to choose lead. From the specs, we could use any of lead, lag, or lead lag. Okay. I'll design a lead controller though. Okay. So we just follow the procedure above. So step one, discretize plant. So P sub D of Z in this case gives us I'm going to run out of time, so I'm going to stop there, but okay. I'll continue from there next time. I've run out of time. I added a script in MATLAB if you want to play around that does this example, right? Just to illustrate that this can be all completely automated, right? You can do this full design just given the plant and the sampling period and the specs, you can just write a script to do all this. But we'll go through it in detail next class, and if you want, you can play around with the script on Learn. Okay, so I'll stick around for a couple of minutes. Otherwise, we'll continue this example next class. So the question is about the difference in oscillations. So negative number to the k, yeah, it's a kind of a behavior you don't see in continuous time. So that basically you can think of it as being, it's the same idea, right? Complex conjugate, except that the point on the circle that you're talking about is -1, right? So you have all these points on the circle which correspond to complex conjugates. This oscillations due to negative numbers to the power of k correspond to you being on the far left side of the circle, basically. You have some number times the negative, and that -1 is just essentially as if you had poles on the circle, but at -1. Or in this case, it would only need 1 in that case, right? Because it doesn't have to be conjugate, but it's the same. It's the exact same idea. It's a point on the circle at -1. It sort of corresponds, if you want to think about it, as the smallest period you can have in discrete time, right? You have a value, the next time step you have a different value, and the next time step you're back to your original value. So your period is two discrete time steps. You can't exhibit any sort of discrete time signal with a smaller period. All right, I gotta go, so I'll see you guys next time. One more question. Can imaginary number oscillations have frequencies other than a complete period every 2 samples? Other than a complete period every 2 samples. So, I mean, it's interesting, right? In discrete time, I don't know if I understand the question, but in discrete time, you can get some funny things, right? Like if you just give me cos of theta k, it's not true that for every value of theta that signal is going to be sort of periodic in some sense, right? What you're going to get, it depends, right? If you get back to where you started. We can talk about this a little bit more next time, but it's a good question. Okay, so I'll answer it next time.